Good evening, everybody. 6 o'clock, I think we can begin. Welcome, everybody that's here, and I wish I could turn the camera on. We have a great crowd here in Times Square, New York at H&H's office, and we have a healthy list of people online. Welcome to the new Scottish Swing Bridge presentation by Barry Keong. This is an IABSE event, one of our many webinars, hybrid events that we like to host around the country, people in person, networking, and a webinar presentation like this that is available to everybody worldwide, actually. I'm going to introduce the IABSE real quickly to those of you that are not familiar. Slide.
Paul and I work really close together.
We do. So the International Association for Bridge and Structural Engineers, IABSE, it's a great organization. I am biased, but I think it might be the best technical engineering, structural engineering organization that exists. It's a very, very hard-working group of engineers. It was established 95 years ago by a group of engineers that wanted to come together and share their experiences and capabilities. And it has grown to over 2,500 members today in over 100 countries. Some of the best bridge and structures engineers in the world contribute to this group. IABSE's mission is to exchange knowledge and advance the practice of structural engineering worldwide. IABSE organizes many conferences and webinars. You're at one of the webinars right now. Twice a year, there's a congress and a symposium. Every year, they're in other parts of the world, from Australia to Japan, the entire world. And they're events where these engineers come together and not only network and socialize and share experiences, but sit down and put pen to paper and work together in one of their committees they may be assigned to further the practice of engineering in the world. IABSE produces a quarterly publication that is one of the best that exists. IABSE bulletins, technical bulletins, case studies, guidelines, and the proceedings to the conferences. Young engineers, I see quite a few young engineers out here. We at IABSE are very eager to bring younger engineers into the fold. Young engineers have great ideas, different experiences, and are necessary for the health of the organization. Just 2 months ago, Sebastian hosted he's here, it's right there, hosted a Meet Your Mentor with Maria Grazia, the president of the US group for IABSE. There's young engineers prizes every year for people that participate. It's open to members under 35, and the fees are greatly reduced. So think about it. The US group for IABSE has the role of organizing events in the US, such as the one that you're at right now. We have over 255 members. And we host the online webinars, the hybrid networking events, the national conference. We have one every year. Joint sessions at professional conferences. American Segmental Bridge Institute is one that we join with quite a bit, and provide newsletters and annual construction site visits. We're looking to be at the Gordie Howe construction site at some point. We're working on that. Maria Grazia is working really hard on that. Some legal stuff. I'm not going to read this to you, but in order to offer PDHs to a group, we have to meet certain standards, and we do meet these. And I don't know if Barry knew this, but Barry's presentation is copyrighted. Hi. And the purpose and learning of this seminar for PDH purposes. It's a new understanding of the engineering design methodology for swing bridges, modern international bridge project experience and lessons learned, as well as some discussion on 3D delivery and how it accelerates the design and the construction process. So with that, I'll introduce Barry Kyung. He's the lead structural engineer for the project that he's presenting here. He actually designed a significant part of this and was involved from the get-go. Barry.
Yeah. All right. Thank you, Paul, for the introduction. Welcome, everybody. My name is Barry. I'll be going over the new Renfrew Bridge here. It's set to open end of this year in Scotland, and walk you through all the phases of the project. So the project location is just west of Glasgow in Scotland. It's about 400 miles to London, 300 miles to Dublin, pretty close to Edinburgh. It's a small little hamlet suburb of Glasgow itself. This project is part of a larger waterfront renewal, like a lot of new infrastructure projects. So there's roads leading up to the bridge itself, and then housing and redevelopment. Currently, this area of Glasgow is pretty industrial. So with those trades kind of being refreshed to more modern schemes, it's all converted over to housing, kind of expanding the neighborhood of Glasgow itself. Originally, the bridge was designed, conceived by Sweco and Cass Hayward and Kettle Collective. They were the concept design team. There was an extreme skew on the pylons, but it was always a double bobtail cable stay swing bridge that you see here. You'll notice that the skew is very aggressive. It led to a lot of engineering and geometric challenges for the project. The nose skew as well was very aggressive. So very complex concept design to actually execute. But taking a step back, should describe what a swing bridge actually is. So typically swing bridges are single leaves. There's a bridge that pivots about a center pier and rotates to allow navigable traffic, and then returns itself back to center to allow for vehicular traffic. Simple motion, but there's a lot of considerations to take into account: wind and operational loads, thermal changes, and things like that. These are all very important factors with determining the support systems for swing bridges. For our bridge, we doubled everything. So we have we have a double leaf cable stayed swing bridge here. So underneath our bridge, we actually support it under 2 pivot piers with a slewing bearing. At the ends, at the abutments, we have end jacks or wedges, and we have a nose lock, which will engage the mating span so that there's continuous load transfer when you drive over the abutment, over the channel, and back over to the next abutment. So a lot of things working in play, but very complex structure. So our solution was a value engineering alternative from the original concept design. We've reduced the skew of the pylons to just orthogonal. The pylons are just straight 90 degrees with the roadway. And we also reduced the toe joint to 6 degrees rather than, I think it was 18 degrees originally. That made sure that we had equal loading between the mating girders left and right. We also had a radial joint as well. So with the slight skew at the nose and the radial joint at the rear, we're able to rotate the bridges freely and operate independently. We do have an unusual 103-degree angle of opening, which I'll get into more a little bit later. So for our superstructure solution, it was a double leaf bobtail cable stay swing bridge. We reduced the number of stays, I believe, from 10 to 6. So you can kind of see everything here. Something to note that Paul mentioned earlier is that we designed the entire bridge in 3D. So the renderings that you see here are not made for renderings. They are made for our contract drawings, and then rendered for presentations and videos, and then sent on to their next life on the contractor's end, and things like that. So this was our engineering model in CAD, which was translated to the owner to make their own renderings. And then this is what the bridge looks like this week. So overall, the design team was led by Graham Constructors. They were the GC. Ramble engineers were hired as the approach design engineers for the civil works and substructure. The entire swing span superstructure and machinery was subcontracted out to what we call the HIJV swing span team. So there was a joint venture between Hollandia Infra out of Rotterdam, Holland, and Amants Smolders, which is based out of Antwerp, Belgium. That was a JV between those two. Hollandia manufactured the South Leaf, Amants manufactured the North Leaf, and then they hired us, which we had another JV of us, Hardiston Hanover and Ronan O'Donovan out of Ireland, to design the swing span superstructure and operating machinery. So a lot of geography at play here: UK, Holland, Belgium, Tampa, Philadelphia, New York, London, Dublin, Ireland, and Australia. So a lot of moving pieces here. It was very helpful for us to design everything in 3D. So this is our bridge typical elevation. We have a 27-meter backspan, 65-meter forward span. When the bridge is closed, it's a 90 by 7-meter navigational clearance. When the bridge is wide open, 90 by unlimited navigational clearance. Our typical cross-section was also simplified in the value engineering. Originally, it was a big tub girder. We simplified that to a more determinate two-girder system with floor beams and orthotropic deck in between. So the orthotropic deck is very lightweight, supported by traditional floor beams. The main box girders themselves are pretty large, about 7 feet tall. So there's access from abutment to abutment through the nose joint inside the main girder itself. And with us being able to leverage cable stay systems and the orthotropic deck, we're able to keep the structure very lightweight, which also meant that we could make it very long, so we came up with more problems that we don't normally encounter, such as aeroelastic stability. So this bridge needed wind fairings on it as well, and drainage. So something that we don't normally typically consider when we're doing a movable bridge. So this is a rough isometric of our bridge site itself. The two bridges rotate about the pivot pier and open to the unusual 103 angle of degree opening. You can see we need to do that because the bridge alignment itself is not perpendicular to the river. Typically, we try to keep the operational angles of swing spans under 90 degrees, but we have two drainage outfalls here as well. So this was the optimal angle to make sure that we didn't run into any obstacles as we plan for future maintenance and things like that. So this is our general arrangement for our superstructure. We have 6 stays in the forward, 6 stays in the rear. It is asymmetric forward and back, which leads to another geometric challenge as well. When you're designing cable stay systems, you do want the 3 points of intersection between the pylon and the 2 points at the deck to be coplanar. So we were able to do that with our 3D model. See a little bit later that our coplanar point of coincidence at the pylon is actually not on a physical spot. It's actually out in space. So we did need to coordinate that a little bit to make sure that the tie loads were balanced. This is the machinery underneath. So the entire bridge is supported on a slewing bearing underneath at the pivot pier. At the pivot pier, there's a machinery room where hydraulic machinery pumps hydraulic lines and electrical equipment to the nose joint at the toe, the movable joint at the toe deck, and then out to the wedge. And then also, because we are asymmetric, we have a concrete counterweight to counterbalance the dead load forward and back. So this is a rough look at the cable stay system. The cable stay system, the business end is really the deck anchorage side. All the strand jacking is done at the lower end that you see here on the right. At the top is the clevis stay anchorage, which is really just for main attachment. This is because the deck anchorage itself is very easy to access from the deck level. So all of that was planned out ahead of time to make sure that for final construction, we didn't run into any issues. So this is a view of our stay anchorage at the pylon and a 3D rendering. Like I mentioned before, because we have so much asymmetry with the bridge geometry, and that the stay angles need to be coplanar. You can see here, this plan view on the section plan on the left is actually cut perpendicular to the vertical axis. So the tie plate is actually not orthogonal with any traditional bridge axis. So very helpful to work in 3D and make sure that everything, or all the points are coplanar and that there's no secondary effects with the tie plates or any other supporting structure. This is what it looks like at the deck anchorage. So the deck anchorage is connected to the main girder. The wind fairing itself is non-structural, installed after the majority of the load is set into the superstructure. So the stay anchorage is just welded to the main girders on the outside, stiffened inside. So the main system under the pivot pier is the slewing bearing itself. The slewing bearing that we used was a ThyssenKrupp Series 19. It's a 3-roller style bearing. These bearings are commercially available. They're typically used for the manufacture of whirly cranes and crawler cranes, something that's just pretty much off the shelf comes to spec, but there's a lot of engineering that gets involved, but nothing crazy that we had to go out and manufacture. This is widely available. This is what the bridge looks like in section, in operation. You can see that the slewing bearing is attached to the bridge superstructure itself, and it's split between the fixed part and the moving part. The bridge is actually operated by 4 pinions run by hydraulic motors that are attached to the pivot pier itself, and they are electronically synchronized in order to operate the bridge. So when everything works right, got 2 bridges moving in unison, letting navigable traffic get through. So for support at the nose and the tail end, we have a nose lock and tail wedges. So the nose lock actually retracts and extends in order to engage the mating span. And at the abutment, a tail wedge engages with a receiver on the abutment side to make sure that we have positive contact and load transfer from the substructure to the superstructure. We'll also notice that the wedge actually provides vertical translation as well. So as we are retracting or extending the wedge, we are lowering the superstructure. This is so that we have proper clearances when we're operating the bridge so that we're not running into any static fixed structure. So this is everything at the rear joint. There's a lot of staggering and equipment and stuff that we had to coordinate here. So it's very helpful to work in 3D. Okay, so this is an anecdote time. When I first started working here, there was a guy who was a year ahead of me. His entire job here was to scan full-size drawings that were 32 inches wide, that were marked up by another engineer and highlighted in red. So he was supposed to receive those by mail, get them reviewed, scan them for record keeping, log them into Lotus Notes, wrap them all up and package them and physically mail them back to whoever made the shop drawing. My first job here was on one of New York City's largest movable bridge projects at the time. And we estimated that we were going to get 10,000 shop drawings, and I was going to be the facilitator for that. And I asked, do I need to look for another job? Because there's no way I'm scanning 10,000 shop drawings. So for that project, it was 2006. We were able to get New York City DOT to accept the electronic delivery of CSS for a bridge in whole. So this is the first real big step of moving into a modern era of delivery. So we're able to use email. At the time, we loved email, not so much now. FTPs and PDFs to submit all the shop drawings. And since then, the delivery hasn't evolved that much. We have cloud systems. Email's gotten worse. Things got more expensive, but pretty much there hasn't been much evolution in those 20 years since then. Starting in the last 5 years, we've kind of stepped it up a lot. PDFs are still our contract deliverable, but to make those PDFs, we're making 3D models, and we're actually submitting step files, agnostic step files as well, in order to make sure that there's additional information. We're still obligated for all the information that is on the 2D contract drawings. The 3D drawings are submitted as a sort of design assist for translating information. Cuts out a lot of RFIs, miscommunication, things like that. And since this was a design build project, it actually helped with execution a lot. So this is the coordination within the Swingspan design team. We submitted our drawings, step files, traditional AutoCAD 2D and 3D, and Trimble Connect, which is a web-based viewer for 3D models. That was submitted to the contractor. Contractor was able to digest that, send back information in a similar fashion so we can kind of coordinate everything. So the big benefit of doing all of this is that once we were at 60, 70%, we could submit the models to the contractor and they can make their prefabrication method statements. So they can start in earnest figuring out how they want to fabricate the bridge before we were done with final engineering, which saved on a lot of rework. They did so much work in 3D that we were able to make sure that the manholes on the right and conduits were bent to the right dimensions before we even delivered the bridge at all. So all of this bending that you see here was included in the 3D model that the fabricator was creating. This is very important because on orthotropic decks, there's a lot of hotspots, very controlled geometry based on the Eurocode. So it's important that we were able to translate all of that. So the contractor, all this process greatly reduced the amount of traditional time that we have for shop drawing checks, since we're basically making our drawings from the same 3D model. Also, the cable stay geometry is very complicated and very difficult to digest in a 2D drawing. You can see here, we have a lot of the different angles and coordinates laid out in isometric and plane 2D, and it does get very complicated. And because we were so concerned about secondary effects within the tie plates at the pylon, it's very helpful for us to actually have a 3D model to send over to the contractor to make sure that we were both understanding the geometry as it was intended. Additionally, the contractor was able to do all of their work plans in 3D using our model as well. So originally we had double fillet welds for welding all of this superstructure here for the pylon. At the lower portions you can see here, there was enough accessibility for welders to get in there and do the internal double fillet welds. Once we get up to the green and blue section up top, it gets really tight. They weren't able to get anybody in there. So we did have to redesign some of those areas to partial penetration welds just to facilitate fabrication, typical things. But we were able to catch that very early on because everyone was digesting a 3D model. So this is some shots of the fabrication there. You can see there's a guy back there further back in the pylon. A lot of access there, but you can see that it does get very tight as we get closer to the top. Another important part of doing a cable stay bridge and a bridge this long is that we're very concerned with deflections. So traditionally on a bridge that we would do here in the States, things are bolted. So you do have some slop in connections to do final alignment of superstructure and machinery. This, because everything was done offsite, we don't have that many chances because everything is welded. You know, you kind of have to take it how it is. But that's where the beauty of having a cable stay system comes into play, because we have such a light, flexible structure. We can actually toy with the final deflections as we are erecting the bridge. So we did construction sequencing design, made sure that we had load cells under all these points here in red. And then we were able to model the predicted deflections of all the super cable stay strands as they were being attached and tensioned. So this is one of the progress shots of the cable stay stressing here, and some close-ups of the anchorage. So it is important with cable stay design that you can add tension, but it's not really good to relieve tension. So you can see here that this is where the jacking occurs for the strands. So a hollow jack will pull the strands, a conical restrainer will bite on the strands to make sure that that tension is locked in. But because that biting deforms the actual cable itself, if we were to back off and relieve the tension, that bitten area has now damaged the strands and is a fatigue hotspot induced area on the cable strand. So it's very important that you only go forward, you can't go backwards, which is why we did so much planning ahead of time. So this is the cable stay clevis that attaches to the pylon up top. Very big equipment. That woman's hand is enormous in real life, but it's about 3 feet. No, I'm just kidding. Very big equipment all the way up top. So it's very important that we kind of have everything planned out and coordinated as well. So geographically, the bridge is pretty difficult, was pretty difficult to execute. The bridge, the North Reef was manufactured in Belgium and then shipped in parts to Vlissingen, Netherlands for final shipping on a barge to Scotland. The South Leaf has most of the machinery, all the nose lock machinery and the movable joint machinery is on the south span. So it's actually very heavy, and that is coming from Rotterdam, Netherlands. All of that gets on a 1-week journey from Belgium, Netherlands out to Scotland. It's about 1,000 miles by sea. For large sub-assemblies and major assemblies of the superstructure, they're transported around the fabrication yards by SPMTs. It's pretty traditional. You guys have seen this, I'm sure, in a lot of projects. Some required special transport engineering outside of the traditional SPMTs. So you'll see here, this is Alex Van Loon. He's a project engineer with Hollandia Infra out of Rotterdam. He is using the 3D model that we developed here that we translated over to his Tekla model for final camber and fabrication, using that digital twin to make the digital twin for the transport engineering. So the image on the right is actually the bridge getting modeled for final transport delivery. So you can see that closely here. At Rotterdam, the quay wall that supports the fabrication yard could not withstand the ground surcharge from rolling an SPMT over it with our bridge. So in that instance, we needed to, even as lightweight as the bridge is, we needed to employ 3 marine cranes in order to lift the bridge so that it could moved safely to a barge. The Matador 3 here in red is the 3rd largest marine crane in Europe. And this is what it looks like in real life. So this is the south leaf of the bridge getting lifted off of the quay wall with the 2 little Matadors in the back. You can see by the shoulder line of the Matador 3 that there is a lot of displacement of the bow of the bridge in order to lift the dead load of the span. But that all went out great, got it onto a barge so it could get floated out to sea. So this is the bridge making its final departure from Rotterdam using another movable bridge on its way to its final home. So those are some pics of the bridge making its way out in the open sea to Scotland. So this process does take a while, but it is faster in this video. So ideally what happens, all the barges come in, roll the leaf off with SPMTs onto the pivot piers. Once we're on the pivot piers, we're on the slewing bearing. The bridge superstructure gets fastened to the slewing bearing itself, and we're able to do the final connections. So prior to this, all machinery and electrical equipment have been installed and tested on the bridge pretty much to 99%. So there's very little work for final movable bridge tie-in of the superstructure at the very end. So did save a lot of time in construction. We could do a lot of work concurrently. So once the 2 bridges are on their pivot piers, just need to rotate them in place with the machinery that we designed. And this is what the bridge looks like 2 weeks ago. And this was from this week earlier here. Going through final testing right now for mechanical functions. More testing as well. You'll see here, final work getting done. All the tie-in work did have to wait for the bridge. So final concrete pours for the abutment, deck joints and stuff like that needed to happen after delivery. But by and large, compared to a traditional bridge project, did go much, much faster. And this is the bridge in the open position as well. So just more functional testing, making sure that everything is going smoothly. You can see that we're standing right over by one of those drainage outfalls here. And this is the bridge, great night shot of the bridge just running here. So in summary, we had a bespoke design to address the site concerns for the owner's requirements. Our orthotropic deck and cable stay system reduced the overall weight of the bridge. 3D delivery helped a lot with progress. And by focusing on prefabrication, we were able to expedite the construction schedule, increase safety. A lot of work was able to be done at project sites in the fabrication yards. And then we also reduced the carbon impact because we're not moving in a bunch of diesel generators to get everything done. So currently, project is set to open to traffic by the end of the year, 2024. And special thanks to our colleagues at Renfrew Council, Graham and Ramble, our colleagues at Hollandia Infra and Mons out of Holland and Belgium, our design partners, RD, out of Dublin, Ireland, and Austria, and all of our guys at H&H Tampa, Pennsylvania, London, and New York. So we do have PDH questions, actually, at the end of this. So what kind of mechanical devices can be used to support a swing span bridge? Anyone? Just yell it out. Nose lock. Wedge. Slug bearing, great. You got all of them. You didn't even need my help. True or false? Each leaf of the Renfrew Bridge can be operated independently. Great. And what is an agnostic 3D file format used in the digital delivery of engineering projects? STEP. And the video here, if you guys have any questions. Thank you. And anyone who's here in the chat as well, feel free to type in questions on Teams. Yes, sir. So the question was, how much time do we save in 3D delivery? Or so the time never really governs the typology of the movable bridge. For the most part, it is elevation of the superstructure, navigable channel clearance, and then substructure constraints is the water level too high, things like that, stuff like that. So this was selected because the owners wanted an unlimited vertical clearance for navigable channels. So there's really either a swing or bascule would have worked here. And then, especially nowadays, substructure work has become very expensive. So if we did have a bascule, we need to increase the amount of size for the substructure as well. So, and we also needed, it was helpful to utilize a cable stay system because the span itself is actually very long compared to a lot of traditional movable bridges. So swing span really was the only option at that point. Yeah. So the question was, what software do we use for the design of the process? And we ran our CAD model out of Autodesk Inventor. Our design models were okay. Our design models were made out of Midas, and then local models were split out from that for analysis. FEA hotspots and things like that were using Lucis. But our CAD model was done primarily in Autodesk Inventor, and our 2D drawings for our contract drawing deliverables were entirely derived from that model.
I see. So I saw a counterweight, a concrete counterweight. What was the size of that, and how was that secured to the bridge?
Everything's in metric, so you're gonna have to excuse me. So the counterweight width was coast to coast with the main girders, so about 7 to 8 meters wide, and then it was 3 bays of floor beams deep, and then the full height of the floor beam. So whatever that is in metric, I don't know what it is in English, but it's pretty much the last half of the tailspan itself was filled with counterweight. The main girders in some of the areas did have a counterweight topping at the bottom just because we needed some extra weight, but we used a little bit of steel ballast and heavyweight concrete to kind of achieve everything, really just making sure that we had everything in a kind of tight and efficient spot because there's just no room. If we did everything in lightweight counterweight, the CG would have not made it to where we wanted it to be. So. Can't see the chat. We have a question?
Okay, the question is from David. Is the carbon footprint lower considering transport of the completed bridge leaves versus local fabrication?
Yes, I think by and large, the carbon footprint was lower. Full-on analysis between the apples to apples analysis between the two wasn't done. But in general, I would say the carbon footprint was lower because we basically just had 1 week of transport for 2 separate pieces rather than 3 years of fabrication and erection in fields. The good part also about the fabricating everything offsite was that the disruption to the local community was minimized. So this is a small hamlet west of Glasgow. If you could imagine all this steel getting trucked in or boated in from pretty far away and getting erected in subsections adjacent to the bridge and then eventually lifted and picked on top of the slewing bearings, it would have had a tremendous impact to the community. So carbon footprint, I can't really talk about the numbers there, but in general, I would say that there was a big benefit to the community and everyone at large for everything being fabricated offsite.
Were there any special considerations in the design of the pivot pier for overturning in the open position? And out of curiosity, how often does the bridge open?
For overturning, yes, there were considerations. That's why we did want to monitor the actual CG of the bridge in the unloaded position very tightly. There's a design limit for overturning of the slewing bearing, which we did not want to exceed and which we didn't exceed. So you could imagine that the design of the slewing bearing used in the crane industry actually has a very large overturning quotient compared to kind of other machinery. So there was considerations for overturning. I'm not sure what the number was, but the slewing bearing itself is fastened to the pivot pier by, Kelly, do you remember how many bolts was it? 180 anchor bolts? 60 anchor bolts casted about 6 meters into the pivot pier concrete and dead-ended with plates and things like that. So very big overturning load, and we just accounted for it in the substructure design. Oh, how often does it open? I don't know. It's not open yet, but this is actually a pretty big, heavily trafficked waterway between Glasgow, and I think it does go all the way to Edinburgh. There is a pleasure cruise you can take from Edinburgh down to Glasgow and out to the Falkirk Wheel, which is not too far from the bridge site as well. So it is heavily trafficked. I'm not sure how many openings are expected, but the vertical clearance is pretty low, 7.8 meters. So I'd imagine it's a decent amount.
What's it? Fine. Thanks. Yeah. All right, that was really an interesting presentation. Thank you.
Thank you.
Yeah, two questions. One, going from the open position to the closed position, were there any alignment or tolerance issues at the center, especially initially? And if there were, what did you do to resolve that? And this is not a very big bridge, but did you involve the likes of RWDI or CPP for any sort of wind tunnel testing? Yeah.
Yes. So for the wind tunnel testing, we utilized CTSB out of France. They did the aeroelastic studies for us. The actual shape of the wind fairing was not the original shape that we actually envisioned for the bridge based off of previous wind fairing studies. It was actually a very unusual shape. You could kind of see that there, you might introduce negative vortices underneath the overhang there, but through our studies with CTSB, we found that this was the most optimal shape for our bridge. And it was very important for us because the front portion of the bridge is actually very flexible because we want to keep it lightweight. We want to keep the dead load of the movable bridge down. So there could be a lot of excitation. So that's why it was very important for us to get all the wind fairing design locked in properly. And then the rear of the bridge doesn't have a wind fairing on it. We're closer to the shore. There's less velocity for the wind there. And also the rear of the bridge, because it has the big concrete counterweight, it's actually very stiff. So we really just have kind of happened upon this kind of elegant wind fairing shape through wind tunnel testing. And I'm sorry, I forgot your first question. Oh, yeah. So alignment is always the biggest headache with a movable bridge. You can design everything as much as you can, but then it's really a guy at the end of the day is just putting a bolt or welding a plate, and it will never be as close as you want it to be, especially for a movable bridge. So that's where the beauty of using a cable stay system came into play. If in execution, we had a deflection that varied from our theoretical, we were able to get that data back from the survey, rerun our cable jacking stages so that we were basically at every stage of cable stay jacking, recalculating what the expected deflections were going to be. So we're doing engineering on the fly as we're doing each cable strand tensioning in order to control the deflection. So if there was left or right imbalance, we could take care of that with the cable stays. And then in the actual thermal design for the bridge, we did take it a step further. Our guys at ROD did the cable stay design, came up with the system with DWDAG, and then for the thermal design of the bridge, we actually ran a lot of different models of if there's sun on this side of the bridge, but there's no sun on that side of the bridge, what are the thermal impacts of all of that? So all of that was encapsulated in the design, and that basically governed what our gap tolerances were for when we're attaching to the joining swing spans itself or the abutments and the joints there. So that gave us our criteria of how far we should be from everything.
Can you tell us a little bit about the joint detail in the middle of the bridge? So the reason I'm asking is
All right.
there will be some, tower leg in the same position will move longitudinally in the opposite direction, longitudinally, which is going to bring the girders back up and down, which is going to cause some kind of torsion. If two towers are moving out of phase, there will be big, sort of, clashing between two edge girders. So I'm not so sure how you deal with that.
Can we take one at a time? You were asking about the nose joint.
Yeah,
Okay.
so joint in the middle, given that we will see some power lag movement back and forth, which will bring girder up and down. If movement are out of phase, two bridges from two sides will fighting each other.
Yeah, so that happens in a lot of twin leafs as well. So I guess to the first part about the nose joint. The nose joint was designed and manufactured by Maurer in Germany. This is the rear joint. So this is the forward joint itself here. So you can see that it's a pretty elaborate system of hydraulic actuators and traditional multi-cell accordion style deck joint pieces itself. So when we operate the bridge, we actually operate the nose joint first. We retract the joint from the south span in towards the south pivot pier itself, giving us that gap that we designed for movement at the deck level. And then we run the span locks and the wedges. The span locks themselves give structural continuity between one span to the next span. So if there was a wind deflection or anything that would move one structure versus another, there's nothing out of phase. There's structural continuity from one span to the other span. So the span locks take care of all of that. The span locks are actually also tapered as well. So if there's some misalignment as the span lock is actuating into its receiver, it will move the span the last couple millimeters in order to make sure that we're locked in. So all of that was baked into the design and shimmable in case we got to the field and things were a little bit off from what we designed.
Thank you very much.
We have questions online. From Dante, he asked, do you foresee cable tensioning adjustment during service? What is the service life of the bridge?
Service life of the bridge is 75 years. Even better. The design life is 120 years for the bridge. And the first part of the question was?
Do you foresee cable tensioning adjustment during service?
Yeah, absolutely. So there's excess tension availability within the cable stay system itself for future tensioning if it ever needs to happen. And that was also part of why the cable stay anchorage system is visually so prominent within the profile of the bridge, so that you don't need a snooper or excess equipment in order to get your strand jack set up out and under the bridge. It's built so that you could just set up some scaffolding and then get a strand jack and a guy out there. So I think if the bridge was a little more architecturally driven, this cable stay anchorage location would be a little more disguised and hidden, certainly probably hidden underneath the wind fairing itself. But for us, we put it there in order for future maintenance and strand jacking availability.
Another question. We got like 5, but I won't do them all right now, but I'll do one more. Neil asked, were Hollandia Imon JV appointed through competitive tender or through direct appointment?
The whole team was appointed through competitive tender.
Yeah, very good. Thanks, Barry. Very good presentation. Just a question. I have 2 questions actually. First one about the wind fairing.
Yes.
Why did you choose the shape exactly? This is a kind of an uncommon shape for the wind fairing.
It is. We had a whole other presentation about the wind fairing, which gets into sort of the aeroelastic results of it. Something that I hadn't really considered we don't normally consider wind fairings in design of movable bridges because they're so short. But since this is long for a movable bridge, we did have to consider it. We found that the overhang actually shed the wind underneath the span and was able to deflect all of the wind so that there were no negative vortices underneath the area between the main girders and the orthotropic deck. So we did play around with that angle. I believe we're at 45 degrees. We tried in the interest of economy and keeping the steel wind fairing smaller. We tried 30 degrees and 15. Those all induced vortices underneath the deck level, the deck area. 45 turned out to be the perfect spot for us, and that's kind of why the shape is like that. And because the overhang area is kind of so low and the bridge itself is so low to the ground, there weren't any uplift or negative vortices in that overhang area itself from the wind fairing study.
Okay, and my other question is regarding seismic. So I know that like Scotland is not very seismic, but let's say you have this bridge in California.
Yeah.
What will you change? We have to change the design to do that. Like, for example, the expansion joint in the middle. Like, could you have like two structures colliding?
Yeah, it's a very interesting question. We are working on a job in Portland right now with the same seismic considerations. I guess the answer is you'd have to engineer for everything. That's what they pay us for. There's no one solution that will kind of keep everybody happy. There are limitations, like financial limitations, site limitations, and things like that. So I can't say offhand what we would change without really knowing the site class criteria, things like that. But seismic is definitely a concern for movable bridges, but I think site specific for each case.
Okay, thanks, Barry.
Thank you.
With each leaf being fabricated in a different shop in a different country, were there any measures in place to make sure that they were within a certain tolerance before being transported?
Yes, that's a great question. So as was noted, each bridge was fabricated in a separate shop in a separate country. The first time that they actually met each other was on site in Scotland. So 3D surveys were taken. LiDAR surveys were taken of the bridge at major construction milestones to make sure that plates were in the theoretical positions that the fabricator originally designed for. All of that was coordinated very well. So this was not the first project that Hollandia Infra and Inmons had done together. They've done several projects together. One company doing one leaf or one half of the bridge, and the other company doing the other half. There was a co-sharing of shop drawings and camber diagrams and things like that. So a lot of that stuff was coordinated ahead of time very thoroughly by the HIJV team in order to make a successful installation in the field.
We have another question online. Dante asks, practically, you replaced the anchor pier with a backspan lock. I noticed you have adjustable anchorages, if I am not wrong.
Stay anchorages? Oh, can I read it?
Maybe I can rephrase it.
Okay.
Did you replace the anchor pier with a backspan lock?
I'm not sure what an anchor pier.
I think maybe what the question is trying to get at is for the support pier in the backspan, right that you showed the video of the wedge being jacked in and out. Right, maybe they were expecting a different type of system based on their experience.
Yeah, we did not. We had an abutment, substructure abutment, and we installed the wedge receiver there to jack the bridge down for seating. So, yeah.
So yes.
Yes. Yeah.
Okay.
I'd say
Next.
yes.
We got more questions online. Neil asks, you mentioned that the wind fairings were required for aeroelastic stability. Can you comment further on this?
No, not really. This is really our incredible collaborators at ROD. We're the principal designers for that system. So I would really just kind of be speaking out of turn and maybe make something up. So I'd rather not do that. So no.
That's okay. That's okay. Next question from Dante. Did you do wind tunnel tests?
Yes, all the wind tunnel tests were done at CTSB out of France. And that informs the final wind fairing design that we have.
Any more questions? Pipe up in the comments.
One more quick question. Was there any wind tunnel testing for the open condition for like maintenance or anything like that?
There was wind tunnel testing. Actually, no, I mean, as I mentioned earlier, with the bridge in the open position, there's a maintenance lock on the shore there. In the Eurocode, especially for movable bridges, there's a provision that if there was prolonged maintenance and you needed to have the bridge open for whatever reason, you need to have a structural secondary system in order to hold the bridge in the open position. You can't rely on the machinery to hold the bridge in the open position. So typically on movable bridges, we would just engage the brakes for the mechanical equipment, and we would just kind of leave it there. In the Eurocode, you're not allowed to do that. So when we were in the open position, the bridge is actually in a very stable setup. It's locked in so you can kind of see here at this bottom right here at the pier here, when the bridge is open, it actually is, we have a second lock bar, vertical lock bar to engage the receiver there in order to make sure that the bridge is fastened down. I think in general, the bridge is much more stable in that position comparatively. So I'm not sure if wind tunnel studies were done for that specifically, but it's less of a concern than in the closed position.
Thanks.
Any other questions?
All right. Well, Barry, that was awesome. Thank you so much for an excellent presentation.
Yes.
And thank you, audience, online and here in person for some great questions. This is a very, very enjoyable presentation. If you have any questions for PDHs or any other items, please contact Faith. And thank you, Faith, for all you did to put this together as well. So thank you, Barry.
Thank you, Faith.